I'm Nikos. I'm a software engineer at Expedia Group, and today myself and Daniel.
Also a software engineer at the Expedia Group.
Today we will talk about reliability engineering and how we attempt to scale it in our company with tools. Yesterday we gave another talk on open source and how open source has evolved in our company over the last 5-6 years since we both joined. Today is slightly different topic. This is our primary area of focus for myself and Daniel. So let's go to the agenda straight away. The agenda for today is as follows. First, we have a few intro slides where we talk a bit about the different models we see in the industry around reliability engineering. We also stress the importance of an on-road experience in the platform space. You have probably heard about a paved road path, which was introduced by Netflix and other companies. It is also what we are trying to do in our company internally. Then we present two of our capabilities and products we are building in those two spaces. That is chaos engineering and the region Failover-as-a-service. And finally, a few key takeaways and lessons we have learned so far. In the two primary models for reliability engineering, we see a reactive model, which is usually the strategy companies adopt first, but also a proactive one. On the reactive side, what we come across is most of the times a single reliability engineering team of SREs, you name it. There are many terms for the engineers nowadays. And then if it is a small company, we have a single team with reliability engineers. It's like a central team. When the company gets bigger and bigger, or in case there are multiple product lines, which is the case for our company, you may see the second submodel, which is SREs embedded into domains. For instance, at Expedia Group, we have many domains. We have flights, cars, properties. We have internal platforms, external platforms. And then there is a lot of context within each of these domains. So it doesn't make sense for us to have only central teams for reliability engineering. That is why we have teams embedded within the domains that have that context. And then we still talk about reactive reliability engineering here. What is the other strategy we find in the industry? It is a more proactive one. The investment there is much higher, and it is usually a strategy that comes after the reactive. In this proactive strategy, the problem you see in the previous model is that there are multiple domain teams, there are multiple reliability engineering teams within domains, and it is pretty hard for them to work together. So they operate in complete silos. And then the whole purpose of this center of excellence is to bring some kind of consistency between and across these teams. The center of excellence, the responsibility of that is to introduce and promote common practices, common processes, common tools. Another team you may find in mostly bigger companies, I guess, is teams building reliability tooling, either building or adopting. That is tooling that can be built in-house, open source tools, or licensed tools. And then if we take the entire model here, what do we have? We have the domain SREs. We have the center of excellence that acts as the bridge between these teams and the teams that are building the tools in that space. What are the tools we are talking about? Maybe this is not very clear. We're talking about observability tools. We're talking about incident management tools, chaos engineering and experimentation platforms, and in general, platform tools, platform health tools. The common approach in the SRE space when building these tools has traditionally been scripting. With scripting, we have a more tactical approach, an approach where there is very limited upfront design. Things need to be implemented fast. There is very limited focus on good practices, testing, on documentation. And this makes these scripts very hard to maintain because they are mostly an action and outcome of a single person. There's a great book which is called Software Engineering at Google, and the authors there identify 3 key differences between programming and software engineering. In our case, we can say this is scripting versus software engineering. And the 3 main differences are scale, time, and one more, which I can't remember. So what do we have here? You can see on the one hand, a more tactical approach, on the other hand, a more strategic approach, right, in software engineering. There is a lot of upfront design, there's an API first approach. There's a strong focus on good practices, on documentation, on testing properly. This ultimately makes these products, because we are now talking about products, not about simple scripts, easier to maintain. They are an effort of a team, and they are maintained by a team. There is investment behind them. In order to justify that investment and have the ROI, the return over investment, it is very critical to bring and to introduce an on-road experience on the platform side. You can see here where we were as a company with the multiple brands. Just to give a bit of a history, Expedia Group was formed through mergers and acquisitions. Many different brands like Hotels.com, Expedia, Verbo Homeway, Trivago, all these brands were part of the company's umbrella, but they were operating completely independently. And the problem we had was multiple runtime platforms, multiple observability tools, multiple service meshes even. And then our strategy over the last year has been to move to a common runtime platform and a common set of tools. What are the benefits of common platforms, of common tools, of this paved road and on-road experience? Those who are familiar with the machine learning space, there is a lot of hype nowadays. You have probably heard about the gradient descent concept, where you're trying to optimize a function, and you're trying to find local maximum or local minimum. This is what this slide shows. And I think this summarizes the whole idea behind the paved road path. You can move from all this local maximum, which would work for us, they would work perfectly fine in the different brands. But we are trying to find this global maximum. And the point here is that even if we do not find the global maximum, we will still achieve better local maximum within and across the company. In the next 2 parts, we have 2 of the capabilities we have been working on. One is chaos engineering, and then Daniel will talk about the region Failover-as-a-service. Chaos engineering, for those who are not familiar, it's not the first concept you come across in the industry, definitely. I'm summarizing this in a single slide. This is a practice that goes back more than 10 years. At Netflix, they introduced this with tools like Chaos Monkey and Kong and all that. Chaos engineering is the discipline of experimenting to ensure that the impact of failure is mitigated. We inject failures to our systems and services and try to understand the behavior of our systems and services. We try to verify a hypothesis. You can see this cycle. One very important concept in chaos engineering is that of a chaos experiment. And in a chaos experiment, we have a cycle which is very similar to the test-driven development. Although we should stress the difference between testing and verification, which is a very controversial point in chaos engineering. In testing, we test known knowns. In chaos engineering, we are trying to verify unknown unknowns. what we have in a chaos experiment is, as a first step, we define the steady state. We form the hypothesis. We introduce the failures. And then the most important part, we verify this hypothesis. We may find that our alerts didn't trigger and we need to fix the metrics or the alerts. We may find that there's not enough capacity. We may need to tweak the autoscalers. And then this may repeat until we are confident about our systems. How it all started for us in chaos engineering, as we said, we were moving to a common platform. And this gives us this presented us the opportunity to consolidate all our tools. We had more than 20 tools used across different brands and teams maintaining them. And these tools would integrate with 1 or 2 platforms only. The return over investment was not that big, as you can imagine. And as we are moving to a common runtime platform, we set up a vision to move to a common chaos engineering platform, which we are presenting in a bit. Most of that is also written in this blog post. You can find it. There are many blog posts. We like to blog a lot in our company. So medium.com, Expedia Group Tech. Now, what is the product offering we have internally right now? We will show the entire architecture in a bit. So let's keep that for a moment. We have a chaos engineering framework. And then we have a single space where we provide a lot of documentation. That documentation is about concepts. What is chaos engineering? What is a chaos experiment? Why do I even need it? And it's very clear. And then what are the tools that we provide as a team internally? We also have a section which documents past experiments. Every time a team runs an experiment, we encourage them to document it into our central space. And like that, we try to build a community. Now the architecture. This is a 30K foot view. Details under the hood for that framework, but how this works is the users are going to see our continuous delivery platform. They add a custom stage in there, which is execute a chaos experiment. And then through Spinnaker, the experiment gets deployed to a worker cluster. So how does this work under the hood? There is an agent that we install in all the clusters, and we have many of them. We expect hundreds of clusters because we have many domains, regions, PCI zones, you know it. The agent we use is an open source project by Datadog. And it's called Chaos Controller, and it's an amazing product. If you haven't used it, please check it out. This is a chaos engineering, or to be more accurate, a fault injection framework. It can introduce failures at many different levels and failures of different types. It enables the execution of chaos experiments using Kubernetes labels to reduce the impact, the blast radius, as we call it, in this space. And then there is a lot of observability, plenty of safety nets, because this is very important in the space. How this controller works, on the left-hand side, you can see the contract. What the contract says here is terminate a set of containers in a non-graceful way. You can see the agent that is installed inside the cluster, runs as a deployment, and then that agent acts on that event that is received. The event describes a case experiment, nothing else. It then spins up these injector pods for a better separation of concerns and responsibilities. There are plenty of permissions needed at that level, and it injects the failure. This diagram is also in the open source project. One interesting challenge we had as a team was, how can we test? How can we debug? How can we show the capabilities of that framework? And what we did was to use a set of what we call demo resources. Some of them are already in the open source project. You can see an Nginx web server that is being called by a curl application every X seconds. And like that, you can introduce failures in the middle, and you can observe the impact of that. We have also created a very simple application with REST endpoints and gRPC services internally to test these failures. Now, what are the different failures that are supported by this agent? When we started working on chaos engineering as a team, we tried to bring some standardization. This standardization is not necessarily there in the industry. In all the tools, you can see that it can do X, it can do Y, but what if we have a better categorization? And the categorization we came up with was these 4 different categories: state ones, resource ones, network, by far the biggest, and then request, mostly at layer 7. On the state side, this controller supports node terminations and kernel panics and container terminations in a graceful and non-graceful way. On the resource side, it supports CPU and disk disruptions. Then network, there is many combinations you can do here, but we can say that it supports dropping packets, corrupting packets, introducing bandwidth struggle, introducing delays with optional 0, which for us is the most important, the one that teams are looking for to verify the behavior of their upstream dependencies. DNS spoofing, and some wider experiments, such as the host level availability zone failures. This works because the availability zones in AWS and the cloud providers, there is a label for them on the node, which means that you can target these nodes only. And finally, request level attacks. Unfortunately, the controller does not support much here. The reason being that most of the attacks are implemented at the lowest level possible on the Linux kernel. It doesn't rely on any service message because this would tie the whole framework to a particular tech. And the Datadog team didn't want to do that. However, there is some support for gRPC, gRPC status code manipulation, which works through a proxy. Okay, what is the architecture of all that end-to-end, what we have right now? The users go to Spinnaker UI, they introduce a custom stage, and in the UI, they provide the fields that are needed to form a unique ID for their cluster. What is the cluster's name? The island, as we call it internally, it's the domain. PCI scopes, things like that. And then the disruption file as well. What is the chaos experiment I want to run? Then, as you can see, we have a set of abstractions in the company until the disruption gets into the what we call worker cluster, the Kubernetes cluster. I have said this part because I don't think it's great to explain that right now, but you can find a lot of information about building Spinnaker plugins. This is what this part shows. There is a blog post on that. How can we scale that? That was always our challenge. You know, this works for 1 cluster, 2 clusters, but if you're a central team and you want to be monitoring such experiments across hundreds of clusters and thousands of engineers and microservices, it gets tricky. One thing we did was to have a lot of visibility with metrics. And luckily enough, the controller itself reports plenty of custom metrics, both the controller and these injector pods, which allowed us to create this dashboard here. And then we can drill down into a particular domain, a particular cluster, and see what is happening. This is not only useful for us because we are not expected to monitor each and every cluster. We primarily provide the tools. But it is very useful for the SRE teams within the domain so that they know what is happening inside their cluster. We also try to scale this by building a community, as we said earlier. Chaos engineering, we understand it is not the first practice team want to have, they have other priorities. We used to be in the application space, both of us, and we know those priorities. So what are we trying to do here? We document, as we said, past experiments that teams have done so that they provide an inspiration for others in case they want to run chaos experiments. And we also talk a lot about that. We talk at conferences, we talk at internal talks, we read blog posts. And that was chaos engineering. I will pass this to Daniel for region Failover-as-a-service.
Yeah, so the title of this tool is Scaling Reliability with Tools. So we're going to talk about the second tool that we built. So this is a tool to evacuate traffic from a region. And it follows the same mindset. So what my colleague Nikos mentioned a while ago about the local maximums and global maximums. So this is meant to be the tool to rule all tools in terms of regional failover. So previously we had a lot of teams, a lot of organizations in the company that they were all individually building their own solution to shift traffic. And that's cool, it works for them. But then if you think from like holistically, like let's say you have a central operations team, and in the middle of an incident, they get a PagerDuty alert, they jump online, and then they need to understand how that tool works that they've never used before. So the idea was to build something to consolidate all of those tools into a single one. So the previous tool, the chaos controller, was about injecting failures. This one is slightly different. So I think there's a lot of analogies with like the automobile, like cars industries. So you have active and passive safety systems. So you have things that are constantly running and trying to prevent an accident from happening, like ABS, etc., right? But at some point, you're going to crash, right? That's inevitable. Things are going to fail. And this tool is focused on that second part. So in the event of an incident, because they will happen, then how do you recover from that failure? So to explain how it works, so Expedia, like it's a very large company, so what I'm about to say, it's not exactly true for every single service, but we primarily operate in US East 1 and US West 2 on AWS, that's our cloud provider. But then we also have presence in a bunch of other regions. But for our critical services, like tier 1s, they all have presence in at least 2, US East 1, US West 2. But for like sake of simplicity, let's just call it like blue and green, and that's it. So those are going to be, for the rest of the talk, our 2 regions. So one important concept that we need to understand, like it's relevant for the other slides, is fault domains. I'm sure you've heard of the expression, what happens in Vegas stays in Vegas. So that's pretty much what we're trying to do. So the point of having these 2 separate regions is obviously the closer we are to the customer, the lower the latencies, right? So the web pages are going to render a lot quicker, etc. But we also try to keep them fully isolated. So the idea is a request that goes to the blue region stays there. Like all of the services that operate in the blue region, they only interact with other services in that region. And the same for the green one. Like there's no cross-region calls. And the point of all this is to create these fault domains. So in the event of a failure, they don't cascade, they don't propagate to the other region. So we have full isolation, or that's what we're trying to achieve. And this is how it looks like. So we have our customers at the top. Usually you have a CDN, like you think Fastly, Akamai, etc. That when the user tries to access our website, they direct it to the closest region. And then once the request enters, say the blue one, it only interacts with the services there. These blue things, this is just, they're not really relevant, but we're heavy users of Kubernetes. So you can just think of these as like deployments or pods there. And we have full set, like the full stack, so data stores, etc. So again, there's no need to have cross-regional calls. So I hope this is making sense. This is trying to represent these fault domains. Yeah, so let's say that there's an incident. And let's say that it's a really big one. Like for some reason, the entire data center is out of service. Like there was a power loss or flooding. Doesn't matter. Like everything on the green region is unavailable. What most companies do, and what XPD also traditionally does, is basically they route or they divert all of the traffic at the edge. And I think this image captures that. So we're shifting, like we're closing the green region. Everyone now needs to go to the other, the backup one, the only one that's still healthy. And you can imagine that there are tons of issues with this approach. This is like the nuclear option, and you can even see in the image there's a lot of contention. So we're shifting a lot of traffic. That's going to result in higher latencies. It's going to result in issues. So if you think that if the entire data center is unavailable, it's not going to be just your company who's trying to move. It's going to be everyone. Like all of the companies here, like Farfetch and Flutters and whatever, they're all trying to rush to the other available region. And what this means is, does Amazon or does Google or Microsoft, do they have enough capacity? Sometimes they don't. So if you wait too long, you'll try to shift traffic and then, oh, there's no more EC2s available for you. So it's a nice option to have, but it's also a nuclear option, if that makes sense. And then we also have, like, what if there's a tiny little incident? It's just a tiny little service that's unavailable. Again, the analogy with roads, like if there's a pothole, we're not going to close the highway, right? It doesn't make sense. You could, but then it comes with all of these costs and all of these risks. So you really need a better approach for this. And this is where our failover-as-a-service comes in. So let's look at our setup again. Same thing, 2 stacks, blue region, green region. But this time on the green region, it's only that tiny little service that's unavailable. So overall, things are still looking okay. It's just that tiny little thing that's not working because, I don't know, someone did a bad deployment or it doesn't matter. But it's a very small failure. So this is what we try to do. Instead of shifting all of the traffic, all of the users to the healthy region, we just divert the traffic of the services that were interacting with the one that's now unhealthy. It does mean that now the Vegas rules, they don't apply. Now there's going to be cross-regional calls. That's not great, but the alternative would be we would be shifting a lot of healthy traffic unnecessarily. So this way, the only impact that we have in terms of higher latencies, etc., for our users, it's only going to be in that tiny little, whatever that may be. It's only going to affect a small number of workflows. This is a very, very simple diagram of how we implemented this. I wasn't sure how much people would be interested in the technical nitty-gritty, and but like I said, we run Kubernetes and we use Istio as our service mesh. So all of these little boxes, they're Kubernetes clusters, and you can see there's some on the blue side, some on the green side, and the little orangey box, that's our mini failover-as-a-service agent. So we deploy a mini container in all of our clusters. And what this container is doing is it connects to a message queue, that's the thing in the middle, and it just listens for instructions. And then at the bottom, you have the operator. So think NOC SRE, like a central operations team, or someone who just reacted to a pager duty, right? So they go into a UI that we provide, they select their service from a drop-down list, and then they just click a button to say, I want to fail over this, all of the traffic from that side to this side or the other way around. And this will send a message to this messaging system that then gets broadcasted to all of our clusters, and then the agent will do the necessary actions to shift traffic. And in terms of traffic shifting, we implemented two mechanisms or two options. One of them is DNS, because it's so easy to do. So like I said, we are on AWS, so this means we modify the Route 53 entries. So very, very basic and very simple to implement, but it does have a lot of drawbacks. So DNS is cached everywhere, right? So even if you click the button, there's a long delay until traffic actually starts moving, because the DNS entries, they need to expire, they need to be resolved again. And then if you think with the HTTP3, with the like gRPCs, etc., you have a lot of long-lived connections or even persistent connections. So, well, I mean, that wasn't a surprise to us, but what we saw was that you click the button and then nothing happens, or it takes a really long time. And by a long time, I mean like several hours. And that's we still have this option, but just as a catch-all. So we implemented this second option. Since we're using service mesh, since we're using Istio, there's a lot of stuff that we can do with Istio. So with the service mesh, we're able to divert traffic at a request level. So the second that we click a button, and after the message gets broadcasted to all of our agents, we are able to shift traffic immediately. And this includes these long-lived connections. And we don't need to worry about DNS. We don't need to worry about any of that. So it's a lot more consistent. It's deterministic. And that's what our teams wanted, the teams that do support and on-call. So again, very, very simple, but let me try to explain how this works. I tried to keep it very light, not very heavy on details. But basically, so the same flow, the user at the bottom, he goes into UI, he picks what he wants to fail over. Is it just a service? Is it an entire cluster? He just clicks some box. And then the message gets broadcasted to all of the agents. And in here, you can see the one on the bottom right that was initially making a call, which is the red dotted line, to a service that's now unhealthy. So that's going to fail, right? And we need to shift that traffic. So what we do is using Istio, we're able to, using virtual services and destination rules. If you want to know more about the details, we can Slack in the hall. But using a bunch of, creating a bunch of Istio resources, we're able to, for that specific service, send it to an egress gateway. So that's the thing with the little arrows. So a egress gateway is just a load balancer that for outside traffic leaving the cluster. And we can send it to an alternative region. So instead of going to the green one, it's now going to the same service that's also running on the blue region. So we have some other capabilities that we're also either building or already part of this this Failover-as-a-service. One of them is scaling up infrastructure. So like I said, a lot of the problems that you have if you try to shift a lot of traffic due to an outage on a cloud provider is about capacity. So we're able to, ahead of time and before we start to shift traffic, we're able to scale up infrastructure. So for example, the worker nodes for our Kubernetes cluster. So this gives our teams a bit more time to look at dashboards, etc., and realize, do we actually need to shift traffic or not? So they're able to reserve capacity ahead of time. The other is obviously scaling up workloads. So since we're shifting a lot of traffic, sometimes even more than 50%, to a region that was probably taking a lot less traffic. Like we need to scale up the workloads as well. So we're able to do that as well. Custom actions. So like I said, Expedia is a really big company, and that comes with challenges of not everything is consistent. So you have teams doing all sorts of crazy stuff. And there's no way that we could provide like to include all of these features and use cases into this tool. So what we did was we created a contract where they can, when their service is being failed over, they can run custom scripts to do whatever it is that they need to do. Say, replicate some database, whatever the use case may be. So this is like a catch-all for everything else that they need to do. And then obviously traffic shifting, but in a gradual way. So we don't want to shift 100% in one go, because obviously systems need to warm up, etc. They need to scale. So we're also building this capability so that we can shift traffic gradually, like 1% at a time, or whatever it may be. And this is where we are at the moment. We started to, I think, run this in production as well. And like I said, the goal is to avoid all of the local maximums, all of this fragmentation of having so many tools doing the same thing, and consolidating into just one. Like if you need to do a failover, go here. That's it. This is going to work for every single service in the company. And we're on to our final slide, key takeaways. So 3 key topics: investing in proactive reliability, consolidate tooling, and focus on customer. So on proactive reliability, Nikos mentioned this in the beginning. Having these central teams that provide tooling for the entire company, that's a game changer, right? You stop having this fragmentation where you have so much duplication of tools, and you can scale these tools massively, and the benefits are huge. And this also applies to tools. So things like fault injection and so on, where you don't just wait for the incident to happen, right? You can play with these experiments. You can simulate failures. Like, what happens if I lose a replica? What happens if I lose whatever, if the network is degraded? And you can identify and fix these issues proactively. Obviously, you need to practice this, and that's super important. Like if you should run game days, you should practice these tools, because you may think that you have all of these tools, but then the day that you need them, maybe they don't work. Maybe the operator doesn't know how to use them. So you definitely need to make sure that you constantly use them and you practice failovers, whatever it may be. The other one, consolidate tooling. So we talked a ton about this yesterday on the open source, and I said that, oh, this applies to other areas, and it does. If you have a lot of tools, then don't. I mean, just pick one and invest in that one. Move all of the legacy systems into a single platform. Because if you think about the investment, let's say you wanted to build Failover-as-a-service, or you wanted to build a Canary deployment solution or something like that. If you need to build this, and if you need to support 20 different service meshes, 20 different compute platforms, that's just crazy. So everyone's going to have a very subpar experience. So yeah, definitely Google on-road or paved road, and you'll see what I mean. And the last one is focus on the customer. Unfortunately, we don't have any photo or any screenshot of the UI of the failover, but when we were designing it, the point was to be as ergonomic as possible, be as simple to use as possible, so as to remove friction from the user, and as to remove the need to have any prior knowledge. Like, they land on that page and they immediately know, just intuitive, what they need to do. So we try to simplify things as much, automate as much as we can, and we run a lot of demo sessions with key teams so that we're constantly feeding back their feedback and incorporating it into the tools that that we built. Yeah. And that was our last slide. So if you have any questions, I guess you can ask them now, or we're going to be in the hall. And yeah, thank you.
Before we close the presentation, just one comment. We should thank all the individuals that were behind those tools, those platforms. There are many, many of them. It's by no means us we are presenting. And also any teams, for example, the chaos engineering team from Datadog, we partner with them a lot. We work in the open, we contribute to their project, and they're amazing. If you guys have this opportunity to work in the open with other companies, it's an amazing opportunity. We talked a lot about that yesterday in the open source deck. That's it. Thank you.